Hello and welcome to this video on the gas laws. Today we're going to take a look at the different gas laws that we actually are going to be using and then we're going to combine them all together. So before we get started we need to know a little bit about how these gases will actually behave. And so we've talked a little bit about gases before, but there's a couple different things that we really want to know. One thing is that gas has a low density. That's why it's actually all around in the air or atmosphere around us. And so what happens is that there's a lot of gas molecules, and it actually, even in this diagram you see here, these little molecules are actually not to scale. They'd be way further apart. And so they have a very large um, volume for a pretty small mass. And so remember, that's our mass density is going to be our mass to volume ratio. And so they have a very low density. One of the other things that we know about gases is that they have the ability to diffuse or to move from a high concentration to a low concentration. And so we know that when they do that, they like to fill up the space that they're in. And so here's before diffusion, we have all of these little gas particles that were added to the mix. You could think of somebody spraying perfume in one location in a room, and after a while, it's going to move throughout the entire space. And so if it's highly concentrated right here, a lot of times our sense of smell or our olfactory senses are able to detect that pretty quickly here, and it'll be stronger. But as it moves out, we'll be able to detect it maybe, but it'll be quite a bit weaker, and then eventually it may diffuse enough that we can't smell it anymore. Effusion is actually where gas molecules can escape through tiny openings. And so we see this in balloons, in helium balloons. So helium is a very small gas. It's actually probably the smallest gas. Hydrogen's pretty small too. And so there's little tiny pores that will be, or holes in the balloon material itself, whether it's latex or the mylar. And so we will see that these gas molecules, when they bump into the outside, so they're constantly moving very rapidly inside here, and if they should happen to hit one of those holes just at the right place, then they can effuse or move out of that space. We actually use helium balloons that have some linings or maybe some special materials to help to prevent that, and so longer lasting balloons have been engineered actually to be able to hold that helium a little bit longer. And then probably the ones that are going to be most important for our gas laws are going to be expansion, and compression. So basically, gases will expand to fill up the space that they have. So we know they take on the volume and the shape of their container. And so if we make that container bigger, they'll fill up that space. We can also push in on that container. We can actually push them closer together by compressing them. We use compressors to do that.
Got gas.
Yes, thanks, honey. So anyhow, here's actually two chambers, and so we can see that we can actually increase the volume, and when we do that, pressure actually will decrease, okay, or we can increase the pressure or decrease the volume. We also know that when this happens, we will see some things occur with temperature as well. And so we don't oftentimes think about temperature. These two actually kind of seem pretty kind of general knowledge, but we know that there's some things that happen with temperature. So this is an overview of the three gas laws. So we see Boyle's gas law is about pressure and volume. So we see here as pressure increases, that volume will decrease, and vice versa. And that's assuming that temperature is held constant. Okay. With Charles' law, he discovered that as volume increased, temperature would increase and vice versa. So I said there's that temperature component. Okay, and that's assuming that pressure is constant. And then on the other hand, if we keep volume constant, we see that as pressure increases, that temperature increases. Now, an important thing to note here is that temperature needs to be in Kelvin. Okay, so we measure gases using Kelvin, and so we're going to have to make sure that we move into Kelvin. So remember, to get into Kelvin, Kelvin is going to be equal to the degrees Celsius plus 273. Okay, and you can go the reverse direction. So Kelvin minus 273 will be degrees Celsius. So you'll need to have that in the back of your mind as we work through some problems today. All right. So let's take a look at how we can actually combine all of these gases into what we call the combined gas law. And here is our equation. And basically what this is looking at is the before and after. So if I think of all of the things that are the ones, this is going to be my before, okay, or my initial, and then my after over here. And so we want to make sure that we can compare what we had before and what we had after. And so there's just going to be slight changes between these three. And as we look at those, one of the things is if we only have two variables that they're asking us for, we would just end up covering up the other one. And so we can basically, if we had something like, say, pressure and volume, then we could just cover up our we could cover up temperature. And so pressure times volume, we could take a look at those ones. Now, say that we wanted to maybe take a look at pressure and temperature, well, then we would just cover up the volume piece here. And so I can cover up volume and I can take a look at the other two. And so we can manipulate that in a variety of ways, which is what we're going to do. So make sure you have this information written down. Remember that temperature has to be in Kelvin. And we are going to take a look at some practice problems, some example problems for being able to solve these. So here's our first one. We're going to start off with 5 liters of a gas under 6 atmospheres of pressure. And we're going to find that it's compressed down to 3 liters, and we want to know what the new pressure is. So I find that one of the most challenging things for students is defining what their variables are here. And so this is, liters is going to be a volume, and this is our initial volume. So this is our V1, okay? And 6 atmospheres of pressure, this is our original pressure. So this is P1. Okay. And we know that we have a second volume that has to be V2, which means the new pressure is going to be P2, and that's what we're trying to solve for. Okay. So I take that combined gas law equation, and I'm only going to use the pressure and the volume. We're going to take out temperature because it's going to be the constant in this case. And so I'm going to put in pressure and volume for each one of these. Now I just want to plug my numbers in. So I'm going to take my 6 atmospheres of pressure, 6.00 atm, times 5 liters, and that's going to be equal to P2 times 3 liters, okay, because 3 liters is what we're going to shrink that down to. All right, so now what I'm going to do is I'm going to just solve for my unknown. If you want to write this as x in your equation, that's perfectly fine. So we're going to divide both sides by our 3 liters, okay, and divide this side by 3 liters. We find that the 3 liters cancels the 3 liters over here, and on this side we have the units of liters are going to cancel units of liters. So I do 6 times 5 divided by 3, and when we do that we find that P2, and I ran out of room down below there, I'm going to put it up here, P2 is going to be 10.0 atmospheres. We started with 3 sig figs in all of our numbers, so we should end with 3 sig figs because that was the least amount that we had. Okay. So that's how you would do one that was just using pressure and volume. Let's try a different one now that's going to use volume and temperature. So we know that our equation, if we remember back, okay, so our equation is P1 V1 over T1 equals P2 V2, excuse me, over T2. So we see in this case that pressure is the constant. We don't have any information about pressure, so we're going to cancel that one out for this, and we're going to use V1 over T1 equals V2 over T2. Okay, but I have to define what I have here. So this one here is liters, and it's the first liters, and I see what's the new volume. So this has to be V1, and V2 is what we're looking for. And then it's if 2.5 liters of gas, and this comes in a pair, okay, at 25 degrees Celsius, this is going to be T1. And then we're going to transfer it into a sauna, so that has to be T2. That's when it's been changed into something new. Okay, now the other thing is we have to remember that we have to have this in Kelvin. So for T1, it's going to be 25 degrees Celsius plus 273, which should give us 298 Kelvin. Okay, I do the same thing over here. So my 35 plus 273, and that should give us T2 value of, let's see, what did I have here? 308 Kelvin. Calculated that earlier for us. So these are the numbers I actually want to plug in. I have to have this in Kelvin. It won't work. You'll get the wrong number if you don't put this in Kelvin. So now what we're going to do is I'm going to plug these in. So V1 is going to go in the spot for V1, so 2.5 liters divided by T1 is going to be here, 298 Kelvin, and that's going to be equal to V2, which is what we're trying to solve, over T2, which we know is 308 Kelvin. Okay, so we just have to define our variables and plug them in. Now I have to solve. I think the easiest way, and there's a couple different ways you can do this algebraically, I think the easiest way for me is I cross multiply. So I multiply these two by each other, and that goes in the top on one side. And then I multiply the other two, so the V2 times the 298. And so when I do that, I get a setup that looks like this. I get V2 times 298 Kelvin is equal to 2.5 liters times 308 Kelvin. Like I said, there's a couple different algebra ways that you can go about that, but I think that's usually the easiest for most students. So now I want to get V2, or X if you want to define it as X, by itself. Okay, so I'm going to divide both sides by the 298 Kelvin. 298 Kelvin. So what I do to one side in these situations, I have to do to the other. So I'm going to cancel these. Okay, Kelvin ends up canceling on this side, and now I go 2.5 times 308 divided by 298. So when I do that, and you want to check this in your calculator to make sure you get the same number, I started with my least number of sig figs. All of these had 2, so I'm going to have 2 sig figs at the end, and I get 2.6 liters. Okay, and that's what I end up with volume afterwards when temperature changes. Okay, let's take a look at another one here. And so this one is going to be with pressure and temperature. And so what we see is that it's very similar to what we just looked at. So now if we take a look, our P1 V1 over T1 equals P2 V2 over T2. We don't have any information in this problem. It says if a canister of gas with 4 atmospheres of pressure is cooled from 45 degrees Celsius to 28 degrees Celsius, what is the new pressure? So we don't have any information about volume, so we can assume that volume is going to be constant, and we can just cross that out. And so what we get is P1 over T1 equals P2 over T2. Now I know this is my P1 because that's what I'm starting with, and it says what's my new pressure? P2 is what we want to know. We're going to start off with 45 degrees Celsius, so that's T1. We have to make that into Kelvin. And then our T2 has to be, we're cooling it down to 28 degrees Celsius. Okay, so I'm going to go ahead and plug these numbers in. So I'm going to take my 4 atmospheres of pressure divided by, now what I usually do is I just add 273 to this temperature, and when I do that I ended up with 318 Kelvin, okay, and that's going to be equal to P2 divided by, and I'm going to add 273 there, and I get 301 Kelvin. Okay. I solve it just like I did before, so I'm going to cross multiply, so these are going to get multiplied together, okay, and these two are going to get multiplied together, and so that gives me P2 times my 318 Kelvin is equal to 4 atmospheres times 301 Kelvin. Okay, so I divide both sides by the 318 Kelvin to get my P2 by itself. Again, if you want to make that into an X, just be very careful with that, that you know which variable you're looking at. These two will cancel, so P2 is by itself now, and my kelvins cancel. I'm looking for a new pressure, which means my units are going to be in atmosphere. So P2 is equal to 4 times 301 divided by 318, and that should give you 3.8 atmospheres. So that's really how you solve most of these. Now, I find that students tend to be challenged if they are looking for temperature in the bottom, and we actually could be given all of the different variables at once. And so we're going to solve a problem that's like that. So this is one that we're going to put all of the different information in, and we're going to be looking for a new temperature. So that new temperature has to be our T2 value. Okay, so that's what we want to know. So we just start off, and these are in trios now. So if a 2.0 liter balloon with a pressure of 0.998 atmospheres at 298 Kelvin is moved, okay, that tells me this stuff is all together. So this has to be my V1, this has to be my P1, and this has to be my T1. Let me see if I can write over the top of this here. T1, there we go. It's moved to a new elevation, so that means this has to be my new pressure of 1 atmosphere, okay? And then it shrinks down to 1.5 liters. So we have a few different things that are going on here. So this has to be, P2, because it's the new, okay? And V2, since it's the new. So you can think of the new thing that it forms as being the 2. So now what I want to do is plug all of these numbers in. So I'm going to take my pressure as my P1. So we remember we have P1 V1 over T1 equals P2 V2 over T2. So I'm going to plug all of those numbers in. So I have 0.998 atmospheres times 2 liters over, and I already have this in Kelvin. That's nice. I don't have to change anything. 298 Kelvin. And that's going to be equal to 1 atmosphere times 1.5 liters divided by T2. And so I find that students get really confused if we see our unknown variable down here. You do the same process. So again, we are going to cross multiply. So we're going to multiply these 3 things together. And we're going to also multiply these 3 things together. And we're going to set those on opposite sides of our equation first. So when I do that, I end up with, let me put that over here. I end up with T2 times 0.998 atmospheres times 2 liters is equal to, I'm going to run out of room, is equal to 1 atmosphere times 1.5 liters times 298, and I am completely out of room. Let me clear that out, and I'll write the rest of it. So hopefully you had this stuff before. If not, go back and look at that again. Okay, so what I ended up with is T2, okay, times 0.998 atmospheres times 2 liters, okay, and that's going to be equal to 1 atmosphere times 1.5 liters times 298 Kelvin. All right, so what we have to do is divide both sides, but now we have to divide by both of these. And so we divide both sides by 0.998 atmospheres and 2 times 2 liters. Okay, so 0.998 atmospheres times 2 liters. And those are both on the bottom. So these are going to cancel on this side because we have the same thing on the top and the bottom. That leaves my unknown variable by itself. I see that atmospheres, the unit is going to cancel atmospheres, and liters is going to cancel liters. I'm left with Kelvin, which is a temperature. Okay. Now, I want to multiply across the top, multiply across the bottom, and divide top by bottom. Make sure you do proper order of operation. So check this in your calculator, and when you do, you should get 224 Kelvin. Now, We started with 3 sig figs. All of them actually had 3 sig figs, so we should end with 3 sig figs. And so that's my double check. Sometimes you'll notice that I kind of knocked off the extra zeros up here in writing that, and I will tend to do that. So that's how to solve gas laws and a little bit about gas behaviors, and I hope that was helpful, and we'll take a look more and explore in class.